Mr. President, members of the jury, firstly, thank you for accepting the invitation to review this thesis work, particularly during such a complicated period for everybody. Ladies and gentlemen in attendance by video, thank you for your interest in this event. It's an honor to present to you today on the culmination of 3 years' work that I've carried out in collaboration with the Université Savoie Mont Blanc, particularly LIBM, and the Fédération Française de Ski, titled Force Production in Alpine Skiers, On and Off Snow Assessment and Relationship with Performance. So the presentation today will follow a typical structure where I'll first discuss the background of the project, followed by 2 experimental aims, each of which address their own overarching aim. I'll then follow with a brief summary and some conclusions for practice. And then, of course, we will finish with a discussion with the jury and the jury. At the outset, it's important to first address the sport of alpine skiing. So alpine skiing is a sport during which athletes must turn back and forth between gates set on a challenging course with the aim of finishing in the shortest possible time. Ultimately, the goal is to finish the season having accrued the best placing and overall best competition points accrued by the governing body, the International Ski Federation, or the FIS. The sport itself consists of 4 distinct competitive events which collapse themselves into 2 disciplines named technical or speed. These disciplines can typically be separated by regulations which create tighter and more frequent turns towards the technical end of the spectrum, and notably in slalom and giant slalom, and then more open turns in a longer course and ultimately faster speeds on the aptly named speed discipline, notably Super G and downhill. And with these regulations in mind, they result in ultimately different technical and physical constraints experienced by the athlete, which tend to make them specialize in either specific events or indeed in disciplines. So skiing is somewhat unique to other sports in that the athlete's contribution to motion, their energy contribution, is somewhat small. Rather, skiing is a story of managing energy conversion. So by that, I mean more specifically, an athlete starts at the beginning of the course with a given amount of potential energy, and their job is to turn back and forth down the course while either dissipating it via friction as heat or converting it into speed or kinetic energy. And so with this initial relationship in mind, it seems somewhat logical, although it can be debated, that over a course, reducing dissipation as much as possible and ultimately increasing velocity, maximizing velocity, would be crucial for success. So with that in mind, one might ask the question, well, simply we just reduce dissipation as much as possible on the course and maximize velocity, and therefore we have the best possible performance. However, it's not quite as simple as that, because for each athlete and indeed each turn, there's a terminal speed above which an athlete cannot ski under control. And in the literature, this is termed the velocity barrier, which I think can be well envisaged as a sort of speedometer, like in your car, with a limiter between skiing in control and out of control, and the underlying variable being velocity. And what's of interest in terms of how we might improve or target improvement in performance is what exactly sets this limiter. And specifically to the focus of this thesis, we're focusing on physical factors and notably force production characteristics. So force production characteristics themselves are particularly important during skiing, since they are the main mechanism through which energy conversion is managed. More specifically, they're applied to turn the athlete or dissipate energy. So with these 2 factors in mind, we start to get a picture of how force application in a given moment can act to either improve or worsen the athlete's performance. And indeed, there's been some research that shows negative associations, so associations between high peak forces in a turn or during a specific section and moments of energy dissipation. However, broader views, so a view over an entire course, for example, and how that associates with performance don't really exist in the literature at present. So to summarize, overall, the current narrative on force production in skiers on the snow is relatively limited, and we don't well understand whether for a skier, skiing better requires more force, or indeed what determines force production on the snow. During a ski turn, there are a number of external forces acting on the athlete. Snow reaction forces are important to research since they correspond to the force production of the athlete and therefore the main changeable force during skiing. Radial or centripetal force is the component of ground reaction forces in response to turning, which itself corresponds to the force applied by the athlete to turn. From basic physics, we understand that radial force is a product of velocity and trajectory characteristics, or more specifically, the turn radius. And with that in mind, we understand that turns performed with a lower turn radius, so for example, a tighter turn performed closer to the gate, or faster turns with the other variable staying constant require greater force production from the athlete. However, if we invert that equation, it provides some perhaps some understanding for how we might improve the performance specifically of the athlete, and that is an athlete who possesses greater force output capability potentially can turn faster or perform turns with a lower turn radius. So having provided a theoretical basis for the importance of force production, the next question is what exactly does force look like during skiing, or more specifically on this slide during a given turn. So we have on the slide here a typical turn from giant slalom with knee angle on the top graphic here, and then the force on the bottom graphic here in function of body weight. And what we're specifically interested on for this slide at least is the black line, which is the outside limb, the dominant limb during the turn. And so during a turn, we see the start of the turn, the initiation, typically corresponds with a concentric action of the lower limbs. We then see an extended quasi-isometric phase, at least in recent research, corresponding with the greatest force during the turn, during the steering phase. And then at the completion of the turn and potentially the transition, we see a reduction in force output and flexion at the knee. And again, notably that we're talking about the outside limb here, and the inside limb is still prevalent with a lesser force output and potentially different muscular actions occurring. Over a course, athletes must produce large levels of force. A clear notable difference, but a clear notable difference to other sports is that these forces are produced at very low angular velocities of the lower limb. So on the graphic here, we have the concentric and eccentric actions of the inside and outside limb, which you can see appear to decrease incrementally across the different disciplines, events which are on the x-axis here. But a notable thing to note from this slide is that even the fastest turn cycling discipline, slalom, doesn't really go above, on average, 90 degrees per second at the knee. And if we look at something like sprint running, we start to get a picture of really how slow forces are produced in this sport. And notably, these graphics don't include this extended quasi-isometric phase, which from the last slide we saw is during which the greatest forces are produced. So with these factors in mind, one way to better understand the mechanical profile of skiers, so their actual capacity for force production, would be to place the expected common field conditions on a force-velocity relationship of the involved musculature. So here we have a typical force-velocity profile of the lower limbs and ballistic extension, which ranges from the maximal force output capability at low velocities as F0, the intercept of the y-axis, and then a linear relationship with decreasing force production to maximum force at high velocities, or V0 here as the intercept on the x-axis. And as it pertains to the lower limb extension, a very important thing to note is that the middle of this relationship approximately corresponds to conditions of body weight, so an unloaded jump practically. Now, if we look at an unloaded jump of typical magnitude and amplitude, we see approximately 300 degrees per second at the knee on average. If we compare that to something like slalom, the fastest turn cycling event, as we saw, we start to get a picture of really, we can almost classify a large proportion of that relationship as what we would expect to be relatively rare in skiing, and rather position both disciplines on the far left end of the spectrum in very high force and very low velocity. So one might expect the surrounding literature characterizing the force capacities of skiers would actually match this theoretical profile that we've built. However, we see two main complications with the current state of the literature. The first is that they typically use relatively limited methodological approaches, more specifically unspecific assessments, assessing force in moderate velocity conditions, for example, body weight jumping or sprint cycling, or potentially more mechanically specific assessments like isokinetic dynamometry, but typically during single limb movements and not very accessible to the general skiing public, shall we say. The second problem is we have overall limited data on the subject, which is a particular problem due to key changes in the skiing realm due to adaptations in equipment and skiing technique that occurred in the early 2000s, which challenges the relevance of older research to the current skiing technique. So at present, we currently have essentially no consensus on the topic of important force capacities for skiers. And further than that, we don't well understand whether there are any discipline-specific differences, what each discipline requires, or indeed each event requires, nor do we understand if better skiers require elevated specific capacities than lower-level skiers. So to summarize, that leaves us with two main problems in the literature regarding force output and force capacities. That is, the importance of force production on the snow is at present unclear, which limits our ability to understand how we might target and transfer training between training and skiing. And then secondly, the force profile itself of skiers is altogether unclear as well, which makes it even more of a problem for targeting training and monitoring for ski athletes. And so a feasible approach to overcome these problems would be, in the first instance, to measure force output on the snow over a broader sampling window and compare this with performance. And the second point would be to test specific force capacities off the snow in the lab in a wide range of athletes and try associate that with performance. And that brings us to the thesis projects. So the thesis itself breaks down into two main themes, as I mentioned at the start of the presentation. The first of which, the first phase, which was targeted on associating skiing performance and force output, and specifically asking whether force output characteristics limit skiing performance. With the second phase focused on associating force output and potentially performance with specific force production capacities. And so I will begin by discussing phase one, which is the on-snow assessment, force output, and skiing performance. This phase breaks down into two distinct studies, the first of which are focused on answering our main questions regarding the association between force output and performance. Then secondly, seeing if we could break those force output characteristics down into dependence on total or technical capacities. And then a second study, which was a purely methodological work, which focused on the validity and reliability of our underlying technologies. So these two studies were part of the same paper, which is in minor revision in PLOS 1 as part of the main study and supplemental data. And we have a number of associated studies, one of which is published by a colleague of mine in Frontiers in Sport and Active Living, and some published abstracts. The approach to this work was we had 15 athletes from a non-homogeneous background, club to World Cup level, ski on an 18-gate giant slalom course, while their performance from start to finish on the course was measured using timing gates. We also measured their instantaneous position on the course using Sports GNSS unit. And then we measured their instantaneous ground reaction force data using a customized set of boot-mounted force platforms. For the analysis, in the first instance, for the positional data, we first detected per turn the cumulated path length the athletes traveled to represent their trajectory characteristics. We then also assessed their energy dissipation as the amount of energy dissipated per normalized the performance of the previous section as velocity in entry velocity. And then additionally, we assessed radial or centripetal force. For the force platform, we measured the total force production, so the summation of the two limbs per turn. and then also characterize differences between the two limb as the magnitude of the outside limb and the difference between the two relative to the total. We then combine these two data streams to provide a novel technical parameter of force orientation effectiveness as the ratio of force, based on some work from sprinting and earlier from sprint cycling, as the proportion of radial force out of the total ground reaction force applied, so FR against FTO. For each variable, we had two distinct analytical approaches. In the first instance, the variable as it represented the total average output across the analysis window, so 14 turns, and then a sectional approach which averaged the variable over distinct parts of the course that were separated based on geomorphological and the characteristics and the intent of the athlete. So the first section where the intent were a moderate relief section where the aim was to gain speed, an overspeed section, a steep section where the idea was to maintain speed, and then a flat low difficulty section as part of an additional characteristic. We then developed an a priori hierarchical model for our analysis. So in the first instance, to detect on our giant slalom course, what was the best variable to represent sectional performance characteristics? So how well did energy dissipation or path length predict or associate with our top level course performance, course time? Level 2, which answered our questions about the interest in force production, and notably radial force on the course, by associating that with our sectional performance parameter. We then asked the question and tried to differentiate the contributors to higher radial force production, whether it was a technical orientation of force as RF, or the total force, which was the total force capability, which was the two parts of that equation. And then finally level 4, whether athletes who produce greater amounts of force did so through either output to the outside limb or a better balance between the two limbs. Moving on to the results for level 1. So on the graphic, on the table here, we have the multiple regression model as it pertains to each of the different sectional sections of the course. So the overall course, speed, overspeed, and flat. And you can see by the highlighted sections there that better skiers on our course actually dissipated less energy rather than displaying any sort of characteristics towards shorter or longer trajectory. So path length did not contribute to these multiple regression models at all. However, in the flat section, neither one of our performance variables provided any discriminatory information for performance. For level 2, we observed that those same athletes who dissipated less energy applied more force in the radial direction. However, similarly, this was unclear in the flat section. For level 3, we found that athletes who produced greater force in the radial direction did so through both a greater total force production on the snow and a greater proportion of that oriented in the radial direction, so a greater technical capability to apply force. However, a key finding from this part of the project was that the contribution of each of these two parameters, so the order in which they were associated with performance, differed depending on the section that we observed. So for example, in the speed section where athletes were gaining speed, it was the total amount of force rather than the orientation, which was the stronger contributor. However, that reversed for the low difficulty flat section. And then level 4, finally, so athletes who produce greater amount of total force did so in the first instance through greater output to the outside limb, and then secondly, reducing the difference between the two limbs. So an important thing to note with that is that it's not simply increasing the output of the outside limb, but rather once the output is increased to the outside limb, emphasizing output to the inside limb to decrease the difference. So to summarize the findings from this part of this phase, in the first instance, we provided evidence that force output is a limiting factor on the snow, and that this itself was dependent on both technical, for the ability to orient force, and total force capabilities. So with that in mind, potentially these findings support the idea that if you are to increase force output, and notably radial force, you might be able to increase that velocity barrier on the snow and subsequently increase performance. However, at this venture, it remains unclear what exactly limits force production on the snow. And with that in mind, what the next phase of the project focuses on is potentially the ability to apply force on the snow is itself associated with specific force capacities. And we ask the question of potentially those capacities vary across disciplines and with performance level. And so I will now discuss the phase 2 of the project of snow force capacity. To recap, this part of the project focused on associating performance and, as we showed, force output in skiing with specific force production capacities, with the key word in that sentence being specific. So the focus of this section was to select important assessments that characterize force in such a way that was relevant to how the athletes performed on the snow. And with that in mind, we can look at the on-snow data to provide at least a basis on which to select important force capacities to assess. So with that in mind, we understand that it's clear that dynamic force production is going to be important, as we see in the turn data. Isometric force production, given that it represents the greatest amount of force output during the turn, at least in regards to more recent research. Explosivity as it applies to turn initiation and potentially in response to deviations in trajectory, unexpected deviations. And then strength endurance, the ability to repeat this output over multiple turns, since skiing doesn't just represent one turn, but an entire course. With this in mind, we created a battery to address these specific capacities. So notably a force velocity profile during both squat and counter movement jump to address dynamic force production at very low and high velocities, and characteristics regarding the difference between squat and counter movement jump to address explosivity, or partially address explosivity. The isometric mid-thigh pull, with the idea of, in the first place, characterizing maximum isometric force, and then secondly, calculating rate of force development to answer questions regarding explosivity. And then a repeated loaded jump test to assess strength endurance in mechanical conditions specific to skiing. The idea with this project was to implement it during both the 2019 and 2020 seasons to increase our sample size as much as possible. However, for reasons that are probably quite evident to everybody, we were unable to meet the aim in the second season. However, we were able to end up with a reasonable sample of high-level athletes, 31 male athletes, approximately evenly spread between speed and technical across each of the different national levels, A, B, and C, within the French team. The idea was to use the athletes following seasonal competitive points as the FIS points to represent their macroscopic performance level, with the idea to further characterize their performance by using a paired on-snow testing, which was originally planned for the spring of 2020. However, similarly, things didn't quite go to plan on that front. With the data that we collected, we then created 3 distinct projects, which in order addressed whether there were differences between disciplines and associations with performance and specific force capacities, whether counter movement provided any additional information to characterize skiers' force production, and then whether we could discriminate between skiers using a ski-specific strength endurance protocol. And I'll first discuss study 3, which addressed discipline and performance differences in specific force production. And this is the topic of an article that was recently accepted into the Scandinavian Journal of Medicine, Science and Sports. The analytical approach to this project we use in the first instance data extracted from the force velocity profile and squat jump, and notably the ability to build up force at extremely low velocities as F0, at moderate velocities as maximal power and also jump height, and then at very high velocities as V0. We use the isometric mid-thigh pull and to extract in the first instance maximal force production during a 500 millisecond window, maximum RFD, and then average RFD as the average rate of force development between pull initiation in the movement and 200 milliseconds as something more reliable and more specific to, potentially specific to what we might be interested in during a skiing turn. To compare our athletes, we of course had to separate them into disciplines, and we did so based on the event in which they held the best standings for their subsequent season. So for example, an athlete who had their best standing in giant slalom, GS, would then become a technical athlete for our analyses. To compare the two disciplines, we used the general linear model, which controlled for performance, athlete standings, and an interaction effect between the group and performance. And then we further tested associations with performance using the interaction effect in the linear model and discipline distinct Pearson's correlations. So moving on to the results. On the graphic here, we have your typical force velocity profile with the power velocity in the background. And in black, we have the technical athletes, and gray, we have the skiers, with the adjoining graphic here corresponding to the data, the maximal force data from the isometric pull. So in the first instance, what we observed was that there were unclear differences for relative measures of force production. So notably body weight, jump height, relative dynamic force and power, and additionally, no clear differences between the disciplines in RFD. However, speed athletes were much heavier. So associated with these non-different measurements relative to body mass, we saw speed athletes produce much greater absolute maximum power, so much greater force at moderate velocities, and similarly, much greater force at very low velocities. Additionally, for isometric force, ski athletes produced much greater isometric force in both relative and absolute means. When examining the associations with performance, in the first instance, what we observed there was no association between force produced at moderate velocities. So more typical assessments that we might see in the skiing literature, maximum jump height or maximum power, no association with performance. However, in both disciplines, there was an association between a more force-dominant dynamic force velocity profile and better skiers. Similarly, we observed an association between greater dynamic force production at low velocities. So here, notably, a negative correlation means it's associated with lower placings, and so better performance, which was stronger in the speed discipline, since it corresponded to both absolute and dynamic force, whereas it was only absolute in the technical disciplines. Similarly, we observed very strong associations between maximum isometric force and performance in the speed disciplines, with just a trend for greater absolute isometric force for technical athletes. And then across both disciplines, rate of force development in both maximal and average capacities was important. Moving on to the implications. So in the first instance, we seem to be able to say from these results that disciplines do differ in specific force production capacities, and notably maximum dynamic force, isometric force, and explosivity were exacerbated or increased in higher ranked athletes or better ranked athletes. With these results in mind, we can tangentially support the theoretical model that we presented in the introduction, since they appear somewhat congruent with what we extracted from anecdotal and on-snow data. With this in mind, the implications for practice are that potentially for testing, it might be important to select more force velocity and more mechanically relevant testing protocols to detect worthwhile changes in ski athletes. For training, it might be an idea to target the development of these specific capacities, so notably force production and isometric means and dynamic force at low velocities. Moving on to study 4, which addressed whether countermovement provided unique information to characterize skiers' force production. So this is the topic of an article which is in minor revision in the Journal of Sports Science. So the effect of countermovement is relatively common in the literature as a ratio between performance as it pertains to jump height or power produced in the countermovement jump against that in the squat jump as a countermovement ratio or CR. So on the slide here we have two athletes, athlete 1 and athlete 2, and athlete 1 has a greater countermovement jump against their squat jump, so a greater countermovement ratio than athlete 2. And the idea here would be potentially the typical interpretation would be that athlete 1, because they have a greater ratio, they're able to improve their countermovement jump relative to their squat jump, that they have some sort of beneficial mechanism, that they have they're better on the scale. However, if we look at the literature underlying the reasons for the countermovement ratio, it would appear that a greater countermovement ratio is in fact associated with a lack of a capability to build up activation and produce force during the squat jump, so a lower rate of force development in the squat jump. So with this in mind, a smaller countermovement ratio might be interesting, and so we could say potentially athlete 2 has something beneficial over athlete 1. So with this in mind, with acknowledging that this countermovement ratio characterizes the ability to build up force to rate of force development without countermovement, the idea was we thought it might provide some interesting or discriminatory information for skiers, since they have no capability to perform a countermovement in their sport. However, an immediate problem that we have when wanting to implement this testing for skiers is that countermovement ratios are almost explicitly assessed in body weight conditions via jump height or power, for example, which, as we know, exist in somewhere around the middle of the force velocity spectrum. However, as we observed in the previous study, skiers exist in very high force at very low velocity, so very disparate mechanical conditions. And we have no clear idea about whether the countermovement ratio as it pertains to the middle of the relationship remains consistent across, so at very low or very high velocities. So before addressing the interest in this countermovement effect for skiers, we first had to test the influence of velocity on this countermovement effect. So with this in mind, we were lucky to collaborate with a Spanish colleague and recruit a cohort of sprinters to test these factors in two mechanically distinct cohorts before testing the interest in this countermovement ratio against for skiers. For the analytical approach, we use the force velocity profile generated from squat jump and countermovement jump to calculate the countermovement effect or countermovement ratio, CR, at very low velocities as CRF, very high velocities as CRV, and then at moderate velocities as CRP or CRH, the ratio between power production or jump height. In the first instance, we assessed the change in the countermovement ratios with velocity by comparing sports across these different variables, and then a pooled correlation between the countermovement ratio at very low and at very high velocities. And then finally, we were able to test the association between skier performance and countermovement ratios using a multiple regression or 3 distinct multiple regression models, which used the capacity for force at a given speed. So for example, at very low speeds, F0, and the paired countermovement effect at that speed, so CRF, and with the outcome variable being the performance as standings. Moving on to the results, what we have here on the slide is each of the different countermovement effects across the different velocities, with the ratio here on the y-axis being presented with 1 being an equal effect, so no effect of countermovement effectively. And then sprinters are in dark gray with skiers in white. In the first instance, what we observed is that countermovement ratios in more common conditions did not separate sports at all. At very low velocities, skiers had a smaller countermovement ratio, so read potentially better capabilities according to the surrounding literature. Then at very high velocities, skiers had increased variability rather, and a higher countermovement ratio. So with these results in mind, as well as a negative correlation between the countermovement effect at very high and low velocities, we concluded that the countermovement ratio provides a distinct view of force capacities across the force velocity spectrum. When associating the countermovement ratio with performance of skiers, what we observed was that better skiers possessed an increased maximum force capacity, which wasn't surprising from the previous study, and a reduced countermovement effect at lower speeds. However, there were no other clear associations within the model for the effect of countermovement. So in terms of the implications of this project, in the first instance, we can say that the countermovement effect appears to differ across the force velocity spectrum, which is incredibly important to understand and to consider when assessing its effect in mechanically distinct cohorts, and notably, for example, skiers. Higher level skiers displayed a tendency towards greater maximal force production, but notably a reduction in countermovement ratio at low speeds. So an idea being that better skiers should increase their squat jump capability relative to their countermovement jump. So we can conclude that countermovement effect does appear to enhance our view of skiers. However, this study was relatively macroscopic, and so more research is needed to clarify the underlying mechanisms, or indeed how we go about targeting the training of this effect. And study 5, moving on to study 5, which addressed whether a mechanically specific strength endurance test can discriminate between disciplines and performance level, which is in preparation for submission to the Journal of Strength and Conditioning Research. So for this test, we implemented a repeated loaded squat jump test, which followed a time to fatigue test, where the objective of the athlete was to maintain a set decrement of their output as long as possible, which was practically set as a cued display to a screen of 10 centimeters of jump height. The outcome variable for this test was the total cumulated work that the athlete performed. What was really a notable part of this project was that we set the athletes in mechanically specific conditions relative to what they performed on the snow. So notably based on some collaborative research recently published in Frontiers in Physiology, we standardized in the first instance the intensity of the movement to what we approximate skiers' experience. Then in the second instance, we standardized the mechanical conditions, so put them in the most force dominant conditions possible, while still maintaining precision in our assessment. For the statistical approach, we first assessed discipline differences using the same model as we employed for study 3, which was a general linear model, which had all the same the covariates and interaction effects, and additionally correcting for slight changes in the mechanical condition experienced by the athletes. For addressing the association with performance, we created a multiple regression model, which in the first instance used maximum force, so the maximum capacity of the athlete. In the second instance, their strength endurance capacity as it represented the ability to maintain a fractional percent of their absolute capability as total work, with the outcome variable being performance or as standings in the different disciplines. In the first instance, we observed in the results from this project was that there was unclear differences between the two disciplines in the outcome variables for this test. Total work did not differentiate between technical or speed athletes. Our multiple regression model was associated with performance. However, on closer inspection, what we observed was that it was rather an absolute capacity for force rather than the influence of strength endurance, which provided a clear model. In the latter case, strength endurance did not clearly or significantly contribute to the multiple regression. So if we're to take these results at face value, it would appear that maximal capacity rather than fractional maintenance of this capacity will be a determinant factor for skiers. However, there are a number of, if not limitations, further questions for this project, notably whether we selected the right mechanical conditions to place the athletes in. There was not a lot of information on the subject to make this decision. And there were some biases induced by the test itself. For example, better skiers jumped with higher loads, and so there was potentially the influence of upper body fatigue, for example. So we need further research on the topic. To summarize phase 2, so in the first instance with study 3, we found that force capacities did vary between disciplines and there were clear associations with performance. For study 2, counter-movement effect appeared to enhance our view of skiers' force production characteristics. And in study 5, we were able to address and test strength endurance qualities in our athletes and provide some potentially interesting results, but we need more work on the subject to provide any clear answers. So the outcome from phase 2, we were able to answer that skiers do indeed appear to possess enhanced specific force production capacities. Better skiers produce those capacities. Finally, moving on to the summary and implications from the thesis. So to provide a summary of the thesis content, we were interested in the association between force output and performance, which we addressed in phase 1, which assessed output and performance on the snow and showed that better athletes on our giant slalom course exhibited greater force output characteristics and better force orientation characteristics. Subsequently, we asked whether force output and performance in skiing was limited by specific force production capacities. We addressed this in phase 2 by associating off-snow profiles with performance via their competitive level as International Ski Federation points. In this phase, we showed that better athletes exhibited elevated specific force production capacities, which appeared to be congruent with the surrounding research. So the main implications from this thesis are relatively simple in that these results indicate that force output on the snow appears to be important, and this might be associated with specific force capacities, notably maximum force production at low velocities, maximum isometric force, and explosivity as RFD and potentially the counter-movement ratio. And since we know from research we can clearly target and develop these capacities in athletes, these results provide a basis for emphasizing their development in testing and training, potentially in the place of more unspecific or technical derivatives. This interpretation is, of course, logical, but narrative on the subject is unclear altogether. So when looking ahead to future work, if we revisit the diagram from the initial slide in this section, those of you who are paying attention would notice that there were different phases of the project that missed a key and direct link between force capacities and that directly assessed on snow. And also we missed associating a clear causal link between each of those different factors: force capacity, force output, and performance. So with that in mind, a clear first step for future research would be to perform matched on and off snow assessments to really and clearly associate force capacities as they exist in the lab and as athletes possess to that they exhibit on the snow and their performance level. The next crucial step following that would be the implementation of training studies that target the development of specific underlying force capacities to then similarly subsequently see whether that results in an increase in force production characteristics on the snow and ultimately performance. Another important point is that there is potential interest in less macroscopic force indices than we use in this PhD project. And there's a potential that those would have further enhanced our view and enhanced the implications of this work. And this is the topic of another PhD student who will be presenting his work very soon. Finally, it's worth considering that this project occurred within the French national system, and so our results might be biased based on a nationalized approach to conditioning. An interesting next step would be a collaborative project across different nations to further clarify the association between physical parameters and skiing performance. So, with many representatives of key Alpine countries on the jury, I think that proposition is a good place to finish. Thank you for your attention.
Thanks, Matt.